Okay, this video is the second in the periodic trends. We're going to cover ionization energy and electronegativity. You've already been introduced to both of those concepts in your group activity. Here we're going to elaborate on them and connect them to that core idea of effective nuclear charge that we introduced in the first video. Okay, so ionization energy is related to the process of ionizing an atom by removing an electron. This is necessarily going to be an endothermic process, okay, to pull that electron off, because of course the electron is stabilized by its interaction with the nucleus of the atom, and you need to put energy in to disrupt that stabilization and get the electron out. So these are always going to be endothermic, and what's more, if you want to do that process a second time to create the 2+ cation, it's going to be even harder, because like we saw with the trends in ionic radii at the end of the last video, if you've already removed one electron, the remaining electrons are going to be held more tightly. You've got the same number of protons but fewer electrons, so there's more positive charge to go around for each of the electrons being held. That's going to make it even harder to remove one more. The amount of energy required for one of these ionization steps is called the ionization energy. The energy associated with removing the first electron is the first ionization energy, and then you've got the second ionization energy, which is always going to be bigger than the first ionization energy for a given atom. Alright, so the trend that you saw in your periodic table, in your periodic trends group activity, was that ionization energy increases across a period and decreases down a group. What I want you to do now is pause the video and take a minute to rationalize that for yourself in terms of the effective nuclear charge idea that we covered in the previous video. Okay, so hopefully you were able to deduce that since the effective nuclear charge is increasing across a row of the periodic table, that means that the amount of attraction for each valence electron to the nucleus is increasing, which means each valence electron is going to be held more tightly, and therefore it's going to be harder to remove, meaning that it's going to have a higher ionization energy associated with it. Conversely, when you're going down a column, remember that the principal quantum number, n, is increasing, which means the electrons are getting progressively further, the valence electrons are getting progressively further and further away from the nucleus. That means they're going to be experiencing less electrostatic attraction, which is going to make them easier to remove. Easier to remove means lower ionization energy. So that's how we can rationalize those trends based on the concepts we covered in the first video. Alright, the next graph we're going to look at. Okay, so this slide is something that you can actually skip if you would like to. It's mostly for students who are interested. It goes into a little bit more detail than I'm expecting you to understand, but provides some insight into how all this electronic structure stuff works. This graph shows all of the ionization energies of the first 86 elements on a single plot. And what you can first off notice is that the general trends that we've been discussing are there to see. If we go across a row, you go from lithium to neon. In the second row, it increases. Sodium to argon in the third row, it increases. Potassium to krypton in the fourth row, it increases, and so on and so forth. Furthermore, if you pick any group, for example, we choose the halogens, you start with fluorine, that's higher than chlorine, that's higher than bromine, that's higher than iodine. You're decreasing down a group just as we'd expect. But the fine structure here is also interesting. You'll recall from the D block video that half-filled and completely filled subshells are anomalously stable. And so what you can see is that if you look at the elements with a filled S subshell, beryllium and magnesium, you will see that it's actually harder to ionize those than the adjacent element where we've started filling the P shell. So when you have just one electron in the P shell, that's easier to take out than it is to break that completely filled S subshell. Similarly, when we get to nitrogen and phosphorus, at that point we have half-filled a P shell. So those are actually harder to ionize than the next one, which is oxygen. So when we ionize oxygen, we actually get to that half-filled P shell. And so that makes it a little bit easier to ionize oxygen and sulfur than nitrogen and phosphorus. You can also see that filling the D shell, we know that's something that we expect to be very stable, and sure enough, zinc and cadmium represent the points where you actually filled the D shell in their respective rows, and those are harder to ionize than you would expect from the adjacent elements. Okay, that's enough. I just wanted to point out these features of the fine structure in the trends in ionization energy. This graph is mostly just to emphasize the huge difference between valence and core. We've talked about it. We've said that core electrons are not available for chemistry. You can basically consider them to be part of a pseudo atom, if you like, where they've screened off part of the proton, so you only have to deal with the effective nuclear charge. And this really helps rationalize that. If you look at this red line, you can see that when you go from pulling out the last valence electron to the first core electron, you get a huge jump in ionization energy. And that's why these core electrons really just aren't available for any chemistry that we might want to do, and for the large part can just be ignored when we're considering the chemical properties of elements. Okay, the last topic for this video is electronegativity, which we're just going to cover very briefly. It's something that's going to be very important going forward, so we want to mention it, we want to connect it to effective nuclear charge, but then we'll come back to it a lot in future units. Basically, electronegativity is how badly, and it's a measure of how badly an atom in a covalent bond that's sharing its electrons wants those electrons to be close to it. Okay, so you can imagine that an atom that has a high effective nuclear charge and is already holding on to its own electrons very tightly is also going to want to hold on to electrons in a covalent bond that it's sharing very tightly, and that's exactly what you see. Fluorine is the most electronegative element that we know of. If we go across the second row from lithium to fluorine, we see that the Pauling electronegativity increases smoothly all the way up to fluorine. Okay, and that's true in the other rows as well. If we go down a column, okay, fluorine is going to be the most electronegative. It's going to be the smallest. Those electrons, those valence electrons, are closest to the nucleus in this column. As we increase N and get further away from the nucleus, the effective nuclear charge is going down. Those electrons are further away. They don't feel the same electrostatic attraction. Okay, so even though the number for the effective nuclear charge stays the same, its effect on the valence electron is decreasing, as we see here, and as you would predict with, as you see in the trend in electronegativity follows the trend in effective nuclear charge. There's the strongest correlation between effective nuclear charge and electronegativity. Okay, we'll talk about bond polarization more in the next section, so we're not going to worry about that right now. The last thing, this is just a graph highlighting what I just said and looking at another trend in ionization energy. Electronegativity is going up across a row, and so what would you expect to happen to the ionization energy? Okay, effective nuclear charge goes up, electronegativity goes up, and it gets harder to ionize. Okay, the difference is that the electronegativity goes up smoothly, while there's a little bit more structure in the ionization energy, but the trend is still the same. And we see that in the second row as well. Okay, that's all I wanted to say about electronegativity in this unit, and that's really the end of the material for this unit. So watch this video and answer the questions, and then the rest of this unit is going to be review.